moving to Dijkstra's algorithm, right? So Dijkstra's algorithm is you're given a graph. The edges could be directed or undirected. Every edge has a weight, has a length. And so then the length of a path is the sum of the lengths of the edges along it, just like you imagine, right? And our goal is to do Google Maps. Our goal is searching. Now we don't want to do the shortest path from one node to another. We do from S. Our goal is to find the shortest path to everything, right? S is your home, and you want to know from home what's the shortest path to get to any other place. All right? Everybody get that, what we're trying to do? All right. I made these in Africa. I remember that. So we're going to do kindergarten Dijkstra's algorithm with castles. All right? So here's our graph, right? And we're trying to, and S is the castle. And what does the king want to do? King wants to make, or the queen, maybe it's a queen, right? She wants to make her people happy. So she needs to find the shortest path from each person to the castle, right? And so here's an example. That's the shortest path. And of course, as I said, the edges have weights. So that path has length 8. And so we're going to store, we might get better paths later. But so the length of this path we've stored is 8. And we need to know how to get back, right? So yeah, I think the capital D's are the actual answer, right, of the shortest path. And then pi will trace the path back, right? So like we did before, for each node, pi of node will tell you how to move backwards to get back to the castle, right? So pi of this guy will trace her way back, right? So everybody can get to the castle quickly when there's danger. And now we're going to set up guards. All right? So we don't build the city all in one day. We're going to build it out, right? We're going to move it out. And so at each particular point in time, there's as we had before, the nodes that have been handled, right, and nodes that have been found. In fact, we're going to assume everybody's found, every node's found, but there's those nodes which have been handled, right? And we're going to put a wall around the handled nodes. All right? So here, this is our loop invariant, is that the castle's in the middle, and some of the nodes have been considered to be found. All right? And then more about the loop invariant. We know that for any node inside the wall, any node that's been handled already, we have the perfect shortest path, right? We have the answer, right? So the D, for each node U that's been handled, the DU gives the length of the shortest path to it. And if you follow the pi's, it will go through all handled nodes and get back to the castle. All right? Does that make sense? That's our loop invariant. Right? So certainly, what's our exit condition? Well, when we've handled all the nodes, then we're going to have the answer. So we'll be done. Right? Now, in the meantime, we're going to have some guards which are going to guard the roads. Because so some of the edges are going to be handled edges. Right? What's the definition of a handled edge? Well, when you handle a node, right, the nodes in the city have been handled, right? And when you handle a node, then you look at all of its edges. We know about the edges from it. So those will be handled edges. And those handled edges we're going to say are guarded by a knight, right? And so so these edges at the edge, right? An edge is going to, right? An edge is handled if it comes out of a handled node. I said that already, right? All the edges, right? All the edges in the city then are going to be handled. And these edges that are leaving the city are handled, right? Why? Because this node here is handled, so all its edges are handled. And so this edge coming out of the city is handled and is guarded. Does that make sense? So if you're in the city, you have all the right answers, and everything is guarded. And all the edges are handled. And then those edges that are leaving the city are also guarded and are also handled. Right? All right, so here I have the orange edges, right, have been handled and are guarded. So, but what about these unhandled edges, right? We've never looked at this edge, right? We don't know this edge exists. We don't know what its weight is. So we can't expect to know anything about it. And so we're thinking that there may be bandits along it, and it's not safe to go along these edges, right? So now let's talk about handled paths, right? We have a handled nodes. The nodes edges out of the nodes are handled edges. What's a handled edge? Are paths, a handled path are paths that go through handled edges. So what are they going to look like? They're going to start at S. They're going to go around the city as much as they want, because those are all handled. And then they're going to take one last edge out, right? That's a handled path. So here you can go around, and then it takes one last edge from a handled node to an unhandled node, right? All right, so what does the path do? As I say, it goes around the city, and it takes that one last edge out. That's our loop invariant. Now, so what do we know? The guys in the city we have the right answer for, right? But the guys outside of the city, these unhandled nodes, what we have is we have the best path that we know about, right? And we don't know about this edge. We've never looked at the edge. So our answer won't talk about that edge, right? What we have is, for each unhandled node, we know the best handled path to it, right? So of the paths that start at S, go through the city, and then take one last edge, right? Of those, we know the best path. And for them, we know the length of this best path and the pi, how to trace it back. All right? So here's an example, right? This path is of length 8. This path is of length 20. Right? Now, what about this poor guy down here? What's his d value? Is there a handled path to it? Right? These are all these edges out here are scary, right? So there's no handled edges to it. So there's no handled path to it. So what's its d value? Infinity. Right? Does that make sense? The best handled path to it, well, there are no handled paths to it. So the length of the best handled path is infinity. So now you might notice that the shortest path to the barn is not this path of length 20. Right? Here's a path that has length 8 plus 5 is 13. Right? That's better than the 20. But we're not storing here 13. We're storing 20. Why is that? right? Because this red path is not handled, right? We've never looked at this edge 5. So it's not included, right? But, that's just what I said. We can calculate its path. It's a better path, but it's unhandled and it's unguarded, so we don't consider it. All right, everybody good so far? Now I'm going to give you a theorem, right? The theorem is that of the unhandled nodes, right? Look at the house and the barn and whoever is out here unhandled, right? And take the one that has the smallest deviation. Oh, another thing I didn't tell you. All edges are positive. All right, we don't have any negative edges. The algorithm doesn't work with negative edges. All right, so you take the smallest d value, right, and that's the little cottage. And what we're claiming is we already know the shortest path to it, right? Here we notice we don't know the shortest overall path to the barn, right, because there was a better path to it, right? But I'm claiming this guy that has the smallest d value is the shortest path. And why is that? Well, suppose there was another path to it that was shorter, right? What does that path have to do? It has to be inside the city for a while, has to take an edge out of the city, and then it has to do something in the countryside, right? But the cost just to get here, the cost in the city and the one last edge, we know is 20, right? Because that's the shortest handled path to it. And then there's this other stuff that isn't going to be negative. Maybe it's 0, but it's not going to be negative. So the length of this path, since this is the smallest d value, this d value is bigger, the length of this path is going to be bigger than 8. Right? So this path here is going to be the shortest path to the cottage. Right? Are people buying this? Yeah? Are people with me here? A little bit? All right, well, the good news is you can come and hear it again in 4 months. All right, so here, any questions about it? Right? What do we got? In here, we have the right answers. For the guy outside, we have the right answer. We have the best answers of those paths that stay inside and then take one last edge. Right? And the d value, the little d value, tells you what is the shortest path that stays inside and takes one last edge. Right? Its length is 8. Well, any path that does anything different than that is going to be longer than 8. So now I claim 8 is the length of the shortest path to it. So we can now say that that's a capital D because we know that's the right answer. And now what do you think we do? Right? We have to handle a node. Remember, the algorithm is take some node that's been found, right? We found a path to it, but not been handled. Right? So all these nodes here have been found but not handled. And remember what we do is we have a priority queue in which we take the one with the smallest d value because we think it's closest to the castle. So this guy has the smallest d value, right? And so we're going to handle it. Right? Our step is we're going to handle, we consider the nodes with the smallest d value and we handle it. Right? We have a priority queue, which, remember how priority queues work? Right? They were heaps. And when you change their priority, they bubble up and down. So here, this is exactly what and we have pointers in and out of the heap. So that's what we're doing here. All these unhandled guys are in a priority queue, which is a heap. And we find the guy with the smallest d value, so it's at the top of the heap. And we handle it. Right? So we handle it, and when we handle it, it becomes part of the city. right? But we also, when we handle it, we have to handle all the outgoing edges. All right? So this edge that's leaving it is now handled, right? So the guard will go away. So when that happens, we have to update everybody else, all the other unhandled guys' D values. All right? So the D value of this has to be updated. And what do we update it to? Well, we want to consider the new paths, right? What are the new paths? Here was what we had before was the shortest path that went through here and took one last edge. But now what are the new paths we're considering? The ones that are in here go one last edge to the cottage, and then go one last edge to the barn, right? Those are the new paths we're considering. And how long are they? Well, the shortest distance to the cottage we know is 8. And the edge from the cottage to the barn is 5. So the edge of this red path is 13. Right? Now that path may be better or it may be worse than the path we have so far. And if it's worse than the path we have so far, then we don't update, right? But if it's better, right, in this case it's better, so then we're going to update the barn, right? How do we update the barn? Here, that was the path to the barn, and now its D value is different, and its pi value, right, is now the cottage, right? So we didn't have to update lots of weird things. All we have to update is when we see that this new path is shorter than the old path, all we have to do is change its D value to the length of the new path, and we change its parent from being used to be the parent was somebody in here, and now the parent is the cottage. Right? Is that making sense? Yeah? So, and then that traces the path back, and we have our new path. And that is the entire algorithm. Right? And so we're good. Any questions about that algorithm? Yeah? Yeah, it is an implicit tree, and the way we store it is for every node to store the parent. The parent doesn't point to the children. The children point to the parent, right? So if here's S, and the shortest path from this node from S to this node is just the one edge. So his pi is S, and his pi is S, and his pi is S, and his pi is S, right? And then these guys, the shortest path is this. So his pi is just going back 1. Right? Does that make sense? So how do you find the shortest path? Now what's the path to this guy? Is you follow the arrows backwards. Right? Does that make sense? Here's the code, because we know we love code. Right? We're given the graph. We're given the S. We want to find the shortest path to every node. And when we find the shortest path, we want to find for every node the pi, the parent, so that we know what those paths are. and for every node, we want to know the D value, all right, which is the length of the shortest path to it. So when we start, nobody's been found except for S, all right? So, and S has been found and not handled. So no edges are handled, right? So the shortest path to S, from S to S, is 0. And you don't need a parent. But the shortest path through handled edges to every other node is infinity. Why? Because we don't have any edges, so there's no paths we're considering. So each of them has a shortest path of length infinity. Does that make sense? And we put all of these unhandled nodes, all the ones that aren't handled, we put them in this priority queue, right? Sorted by their d values. So in the priority queue, what's in there? There's S with priority 0, and there's everybody else with priority infinity, right? So then what does the algorithm do? Well, it takes the guy with the highest not the highest priority, it takes the guy with the lowest v, right, and handles it. So who does it handle first? Well, S has a d of 0, so that's who it handles first, right? And so it keeps doing that, and now at some point it takes U from the priority queue. And who does it take from the priority queue? It takes of the people, of the buildings that are in the priority queue. They're the buildings that aren't been handled. So they're not in the castle yet, right? We have their d values. Of those that are in the priority queue, we take the one with the smallest d value. All right? So we take U here from the priority queue with the smallest d value, and we handle it. How do we handle it? Is we look at every v if there's an edge, right? If there's here is U, we're going to handle it. We look at every edge v, right? And what do we do with that v? Well, we calculate what's the length of the new path from S to v. The length of the new found path is the length of the path from S to U plus the edge from U to v, right? So that's, here we have this new path. Maybe we had a different path before that was to v, but now this is our new path, right? So then we find, hey, is the new path shorter than our previous path, right? Remember, dv is the length of our previous shorter path to v, and this found path length is the new path to v, and we say, is it shorter? And if it's shorter, we update. The d value becomes the length of that new path, and when you change the length of the path, the length of the d in the heap changes, right? So v's priority changes, so it bubbles. It's getting smaller, so it bubbles up the tree, up the heap, right? And we change the pi of the v to be, v is now, his parent is now u, right? Does that make sense? Are people kind of following? And and then u's now been handled. So we take it out of the queue, and we say it's now wherever we put handled guys, right? And in the end, we return the answers. And then you'll note that the guys you've never found will keep d values of infinity, and that's it. So here we're just doing it again by with the picture, right? So maybe this is our graph, and these are our handled nodes, right? And these nodes have been found but not handled. And which are the handled edges? Sorry, they're black, so you might not be able to see them, right? But these edges, those paths form the handled edges. So what's the shortest? What are the handled paths? Oh, now they're red, so you can see them, right? Those are the handled paths, and so now we want to say, right? And the d values out here give you the shortest handled path, And for the handled nodes, you got the shortest overall path. Right? And so now there's some node here that you haven't noticed yet. Right? So its d value is infinity. And note that this path, V, the shortest path that we handled path, is this. Right? That's the shortest path we know about. Is it the shortest overall path? Well, look at this path. That might actually be shorter. Right? We don't know about it because we haven't considered these edges. Right? Does that make sense? What's our update? Right? We handled the guy who seems closest to S, so the shortest handled path to, right? Right, so of these guys, right, we have a shortest handled path to V, we have the shortest handled path to U, we see which one has the smallest d value, U has the smallest d value, so we look at that edge, and then we look at the length of this path, right? So what's the shortest handled path to V now? Well, it's either the path we had before, which is this, or it's the new path, which is this. Right? And we make it to be the smallest of the two. Right? Are people good? So now we can trace through an example. Right? So we start with the d value of 0. And when we handle it, right, everybody here has a d value in infinity, right? So when we handle S, now these edges are handled, and the nodes S is handled, and so these d values got updated, right? The shortest handled path to C is, well, you take that edge of length 40. Right, everybody good? These guys here are infinity because you can't get there through an orange path. Yeah? Oh, the whole reason we're doing this, when we did depth first search, it worked when the edges were length 1. Right? But now every edge has a different length. Right? So we're given this graph with these edge weights. Only thing we know about the weights is they're not negative. All right? So then who has the smallest d value? Right? A has the smallest d value, so we handle it. And when we handle it, right, that now becomes a handled node, so it's going to be black, which, sorry, you can't see. But these yellow edges were unhandled, and we make them handled. And we update the d values, right? Because here this guy used to be the shortest path was 40, but now it's going to be 1 plus 30 is 31, right? And this path used to be infinity, but now it's going to be 1 plus 2 is 3, right? So here we get the 31, and here we get the 3. Is that making sense? Right? And then we say, who has the smallest d value? Well, it's F. So we're going to handle F. By handling F, that edge becomes black because it's now the fixed path. And these edges here weren't handled, but we're going out and we're handling them. And you'll note their d values get updated. Right? To get here, it takes 3. 3 plus 15 is 18. That's why this number goes down to 18. Right? And here, 3 plus 1 is 4. So this is going to go in from infinity down to 4. Right? And then we say, who's the smallest d value? It's 4. And so we update those guys. Right? Again, here's a bunch of values that get better. Right? Those are better paths. And then we say, who's the smallest d value? It's d. So this gets updated. Right? Here we had 10 here, but 5 plus 2 is 7. So this is a little bit better. Right? Is that making sense? And you keep doing this, and eventually you're done and you get the answer. So here, these guys, right, now the smallest d value is infinity. If we update it, it just gets infinity, infinity, and it's not a big, and we're done. Does that make sense? Oh, and I really do try to have different tests every year, but some questions I'm lazy. And I must admit I've had this exact question on so many tests. You know, and every time half the class gets it wrong. All right? So let me tell you the answer to this question. All right? So here is what we're saying. I'm telling you that this is our graph. These edges are handled. So I want to know what the d values are, right? And the d value of this is 0. Oh, A is our s, if you didn't figure that out, right? And then, right, those are the shortest path. These are the shortest path to the guys. Those are the right answers, right? This is the best path. This is the best path. Those are the right answers for the guys that are handled, right? But now, what's the d value for E, right, in C? So here, 19. So 13 plus 8. Right? What do we got here? Right? So this guy is 6 plus 1 is 17, and this guy is 13 plus 8. Oh no, here we're going 16 plus 4, right, is 20. Yeah, so this is where we're going to catch who knows what's going on, right? So is this d value, is it 20, right, because that path, right? This 20 comes from 16 plus 4, right? 13 plus 8 is bigger. But look at this guy. This path is 17 plus 2 is 19. It's better. Why isn't that number 19? Exactly. This edge here is not guarded, right? It's not available. We've never looked at this edge. How could we possibly take that edge into account? We've just never looked at it, right? So what the d value is the shortest handled path. So a handled path, it goes through the handled nodes, right? Here, we go through the handled nodes, and then it takes this one last edge, one last handled edge out, right? This edge is handled because it's coming out of a handled node. This edge is not handled because neither of its nodes have been handled, right? Does that make sense? So that's the picture. What is this guy's d value? Infinity. All right, what does the algorithm do next? No, there's more. What does the algorithm do next? Yeah, it takes the smallest d value. The smallest d value is 17, right? So we handle it. And how do we handle it? Is we include it into the city. And then we update. Now that guy gets updated to 19, and that guy gets updated to 17 plus 20 is 37. Right? Does that make sense? And that, right, right, E's d value is C, and D's d value is C. No, pi value, right? Sorry. D's pi value, his parent is coming back here, and this guy's parent is coming back here. Everybody got that? That's the question. All right? So now again we want to do the running time, right? So every time we do an edge, what happens when we do an edge? We update a d-value, right? When we're handling when a hedge becomes handles, we update the d-value. And when we update the d-value, we have to do this work, which is not a big deal, but we have to update the priority queue. And how long does it take to update the priority queue? Log n, right? So the running time is the number of edges times log n. Good? N is the number of nodes because the heap it has a d-value for every node. But of course, the log n and log e would be the same, so it doesn't really matter. And we're doing this heap stuff, right? We did this already, right? You've seen these slides already. We're changing the d-value. Everybody kind of remember that? They're in the bottom, and if they eventually, right, that's what I had that example here. Right? These guys you're never going to connect. And at some point, the handled guy with the smallest d-value is infinity. And so then you handle it, and infinity to infinity is infinity, and it still works out. All right. How are we doing for time? Can we go home yet? We go to 9, right? So that means we go to 10 to 9. Somebody do the math. What do we got, 14 minutes? We can finish graphs in 14 minutes. We're going to finish graphs, I think. All right. Now we're going to do it